studied relativity under Dr. Wolfgang Rendler, who teaches or who taught at the University of Texas at Dallas. And so I have a little education in that area. I've always been interested in physics. And I realized that my stance in believing SRT, or special relativity theory, is not very popular here. So don't throw darts at me. Give my presentation.
Point that to the computer.
Here's an outline of my presentation. I'm going to show analogies of the electric field of a charge to the gravity field assumed of a massive object. And the hypothesis in this is that there is a gravity field. That's one of the assumptions. And because I'm using special relativity theory, that is based on four-dimension flat space. I think we call it the Minkowski space. Then I'm going to show an outline of the SRT formulation applied to the electric field and to the gravity field. Then I'm going to outline a computer program to calculate perihelion advances. I devised a computer program in Pascal and ran it, and to my surprise, it worked. And I'm going to show some uses of this approach to gravity, and then some possible cosmological implications. Now here's the analogy of the gravity field to the electric field of a charge. This here is the Newton gravity formula, and there is the Coulomb force, and you can see the terms are quite similar, and we define an electric field by this quantity here, so we can define a gravity field by this quantity. And then to get the forces, we can just add mass, multiply the gravity field by the mass to get the force of gravity. And similarly, we can get the force, Coulomb force, by multiplying the charge by the electric field. Now, I'm sure Lucas would have consternation right here when I describe a field originated at a point charge. I'm using a mathematical point to describe the electric field. Also, the electric field does not terminate at a sharp point. It goes out into infinity, where it terminates on another charge or goes off into space somewhere. Now, flux density or intensity of the fields is uniformly distributed for a stationary charge or mass and varies as 1 over r squared. Let's see. Now, these, I'm going over the basic postulates of special relativity. The first one, the relativity principle, and all inertial frames are totally equivalent for the performance of all physical laws. Now, most of us don't have any problem with that one, but we have, a lot of you have a lot of problem with this second postulate. That light travels rectilinearly with constant speed c in vacuum in every inertial frame. And that's where a lot of the MPA dissidents get off the bandwagon. Anyway, I'm staying on it. And the velocities are relative to a stationary observer, and a stationary observer can be like a stationary charge or a person or anything that the other inertial frame is moving relative to. Now, the Lorentz force law is the starting point for the four-force SRT transformation. And in the textbooks, the relatives start with this Lorentz law. And you notice that, well, usually this applies to a charge like moving in a cathode ray tube where there's an electric field and a magnetic field. But in my analysis, I'm just going to start with this first term right here, the QE. Force is equal to Q times E. And then we'll see how E, the electric field, is transformed with the Lorentz transform. And I don't think I have to define these terms here. V is always the relative velocity. H is the magnetic field, and E is the electric field. It could be EG for gravity and EC for electric. Now the transformation, the results by omitting the extra magnetic field source of the Lorentz force is this term right here. You see we got gamma factors in here, and gamma is, as you know, 1 over the square root of 1 minus b squared over c squared. And we got a sine theta there. Did I miss, I might have missed it. Yeah, I missed something here. Oh, I'm going the wrong way. Okay, I guess it didn't. Now for the gravity field, it's the same as this transformation, except I add a gamma term right here for the mass, because the mass increases with velocity. And that's the difference between these two. Charges are invariant in transformation, and masses are not. Now this is a pictorial 3D representation of the fields. The radial distance, like from the point here to the edge of the circle, represents the intensity of the field. And this is a cross section. Try to visualize this as a solid. The circle is a sphere, and this is kind of an oval solid right here. This part right here represents the length contraction of the electric field. Notice that it's augmented in the perpendicular direction to the velocity of the particle. And also notice that it's reduced in intensity in the direction of the particle, and also in the aft direction. Now, the Biot-Savart law ignores this part right here in his equation right here. And that's due to the cross product term there. And because it goes to zero when you go down to the direction here. Now, what it turns out to be is that this shaded area here represents the magnetic field created by a moving charge. And probably a lot of you have trouble with that idea. But I was able to, using this technology, derive the old Ampere law. The old Ampere law shows that there's longitudinal repulsion in a current carrying wire. And Peter Grinnell demonstrated that by blowing up wires with heavy current. Well, let's see. Now I take that formula for the gravity field, multiplied by M1, and I do a reduction on the complicated terms there. This theta here is the angle between the radial vector and the velocity vector. And I do a binomial theorem reduction by eliminating high-order terms to get this term here. So you might say that this is a new formula for gravity with a slight modification of Newton's gravity law. Now we'll divide that into two different components, that law. One of them is the Newton force. You recognize it. It's multiplied by that one term. And the SRT force is that second term, and its main components are V squared over C squared. And it's got that theta direction too associated with it. And your pure GR people, they won't admit that a planet is the gravity field is velocity dependent. So I devised a computer model to test this out. The SRT excess force was tested in a computer program to see if this force, in addition to the Newton gravity law, would produce the Mercury perihelion advance. Now, at the Mercury perihelion, or perigee, whatever you want to call it, the ratio of the SRT force, FSRT, to the Newton force, called Fn, is calculated to be 3.86 times 10 to the minus 8. Now, that's what relativity does to the Newton force, which is hardly noticeable, you know. So the SRT force is very small compared to the Newton force. Therefore, as an engineer, I can approximate things. I can use the Newton force and a pure elliptical orbit to calculate the velocity of Mercury and the time between segments and so forth. The Newton force dominates and is used to calculate the main parameters of the elliptical orbit of Mercury: position, velocity, and time. And the elliptical orbit is broken in piecewise into 80 segments, and calculations are performed at each segment. And in this program I used 15 digits for the computation, significant digits. The SRT force produces a small acceleration on Mercury and a small displacement. And this acceleration is defined by F SRT over the mass of Mercury. And this acceleration is reduced to two components, one in the radial direction. That's one from Mercury toward the Sun, and then one perpendicular to that radial direction. Then these small, then you do double integration on the acceleration to get distance, and I don't know, this formula was in my freshman physics book. And I use that, and the distance at each segment is calculated as the acceleration at that point times t squared over 2. And then you add the initial displacement. And you do that for the radial direction and the perpendicular direction. Now, at the end of computing over one loop, the two small accumulated perpendicular distances are combined, and then we need a R here. If you think of a circle, you know, 2 pi r is equal to circumference, then the radius then is well, let's see, the delta S of the circumference divided by r is equal to the angular displacement in radians. And a suitable r is obtained for the ellipse by averaging the lengths of the semi-major axis and the semi-minor axis. And r is equal to a major plus b major divided by 2. Now that's a straightforward way to calculate that without going through all the math that Roger pointed out.
Which Roger?
Then the computer model extends the angular displacement of one elliptical orbit of Mercury to the angular displacement of Mercury occurring in 100 Earth years. And the following table shows the computed results of the program for Mercury, Venus, and Earth. There it is. Now, the computed program for Mercury, I came out with 42.6 degrees. Arc seconds per 100 Earth years. And the GR calculated is 42.98, given a difference of minus 0.89 arc seconds per 100 years. And I just plugged in the values in this program for Venus and Earth, and the computed advance is 8.18 for Venus. The GR calculated is 8.62, the difference being minus 5.1%. And then for Earth, it has a slight elliptical orbit. 3.63 compared to 3.84, a difference of minus 5.5%.
The fact that the difference is 8.16 and 8.62, that is 0.51.
Oh, it's
correction. Subtraction mistake there.
Your decimal point is off on the difference.
Where?
8.18 and 8.62. On Venus.
On Venus. What's the difference between 8.16 and 8.62? It is not 5.1.
It's not a percent.
Oh,
it's a percent.
My apologies.
It's a percent. Sorry about that.
Now these error differences amount to an average of minus 0.34 arc seconds per 100 Earth years for the computer model as compared to the GRT values. Now, I'm not saying that GRT is right or not, but
So we don't need general relativity, is that the conclusion?
huh?
So the conclusion is we didn't need general relativity.
Well, I'll go on.
Not yet.
The gravity laws for high relative velocities of mass, this formula is good for velocities up to c. I'm sure somebody will disagree with that, but if the masses are receding from each other, then the sine theta term here is 0, and so you only are left with a gamma term in the denominator. So high velocity as well as large distances decreases the gravity force. Now the uses of new gravity law may explain why rockets launched vertically travel further than predicted by Newton's gravity law. Also, the weight of a vertically rotating disk, rotating in this direction, will be non-uniform. The sides here will be lighter, and the top and bottom will be heavier, and the sides, will be lighter. And a horizontally spinning disk should weigh slightly more than the same disk spinning vertically. Now that's, we're talking about, 10 to the minus 8 type weight changes, very small. And so the gravity law also gives supports for the SRT derived electromagnetic laws and vice versa. And I derived in the previous paper the electromagnetism laws from SRT. And it has possible cosmological implications. Here are some possible cosmological implications. Space is Minkowski flat, which would suggest that the universe is infinite. However, cosmologists who believe in GR recognize that our space is flat now. They've made some tests in the past using the cosmic background radiation and to determine whether it spread out or converges or is flat. And they say it's mainly flat, so it just might be slightly curved, at least that's what they say. And I've shown that gravity is velocity dependent. I knew a doctor that came out of Notre Dame in physics, and he told me he didn't believe that gravity was velocity dependent. And he liked the beauty of the equations of GR, I think. So anyway, I believe I've shown that, at least in our part of the universe. And so we can view the force of gravity as being due to mass and inertia, versus to have use of concepts of geodesics and curved space. And GR might be used in the microcosmic region, and SR might be used in the macrocosmic. Now this is the end of my presentation, and so I'm open for any questions.
Can I apologize once more for interrupting you?
Can you what?
Can I apologize once more for interrupting you?
Oh, no
It's
problem.
not necessary. We all do.
No, it does.
Have used a perturbation theory.
What?
Your method has been used a perturbation theory. Perturbation.
Perturbation theory?
Yeah. True. But in general relativity, there's no perturbation theory, because any two-body problem has no bounded dynamic solution. If the solution is not bounded, you can't do a perturbation. So what I'm saying, your calculus is correct under certain circumstances. If you can correct the early part, justify it, then you're right. If you have not been able to correct the early part, then just as Gustron said, the chairman of the Nobel Prize from 1922 to 1929, Einstein's calculation is invalid. In other words, your calculation is invalid. So is this gentleman's arguments all invalid. All invalid.
Which gentleman was that? Which Roger?
What was the question?
He says that to everybody, don't worry.
Yeah.
Are you through?
I'll give you my presentation later.
Valid, okay.
The effect that we're looking for is very small.
What?
The effect that the rate of change of the precession of the perihelion of Mercury is fairly small.
Yeah.
That we're looking for. And so they've made a number of idealizations. For instance, the orbit of Mercury is tilted with respect to the equatorial plane of the sun. That produces a measurable effect. You have not included that. Also, you have not included the fact that we know how to derive from electrodynamics the acceleration term for the force, for the electromagnetic force. You've neglected the acceleration term. These terms may cancel one another to some extent, but they're larger than the effect you're looking for. So you can't do such a simplistic calculation. You have to take into account these things that are as large or larger than the effect you're looking for.
Okay, well, like I say, I'm a believer in S or T, and I really don't approve of your cross products in your equation, and also I don't approve of your acceleration term. In SRT, velocity, how acceleration affects velocity, and it's velocity that affects the forces here.
Well, just for instance, take that sine squared theta term that you had in there. Because of the tilt of the plane of the orbit, you didn't take that into account. It produces a measurable effect. And you have neglected it, and so has many people. Because at the time that was done, we hadn't measured the tilt of the orbits with respect to the equatorial plane of the sun. And after we measured it, people did not want to go back and do that because then it messed up
Well, I
the
don't
agreement with
see
general relativity.
offhand how that's even relevant.
Any other questions?
Any other?
Sorry. So, like, my criticism is you haven't properly explained what you mean by special relativity, because I've talked to lots of people about special relativity and they come up with different descriptions of what's going on. Just stating what the two postulates are isn't enough, because the people start forming different opinions as to what those things mean. So just saying all this comes in special relativity, it's vague really, because people just will say give different answers to things like the twin paradox and everything else.
Yeah. Well, special relativity defines what occurs in one inertial frame that's moving relative to another inertial frame. And there's generally uniform velocity, or it doesn't have to be uniform velocity, it can be instantaneous velocity. And you're able to transform with the Lorentz transform from the moving frame to another frame.
Well, you can do that for the Lorentz theory. You don't have to do it from Einstein's 1905 theory.
And the claim is that the laws of nature have to be Lorentz invariant. In other words, from the transformation from one frame to the next frame, the laws have to be concurrent. And have the same form is what they mean. I'm not sure that explains it all. You get, with the transformation, you get time dilation and you get length contraction.
Yes. Well, see, this is where I would disagree with Lorenz directly, because Lorenz is assuming a moving object and a stationary object. There's no such thing. They're both moving relative to each other. If you're on the body moving at close to light speed relative to the other one's moving at close to light speed relative to that one. So whichever one, if you're a body on either one, you may see an apparent shortening, but you can't because you're both shortening. So it remains the same. The fact is that all of these things assume a stationary object when there is none. If I'm moving away from you by close to light speed, you're moving away from me at close to light speed. So the effect is negated.
But from your perspective, you're still...
No, but from his perspective on the other object, he sees me shortened.
Right.
And I see him shortened.
That's right.
Right.
That's not a contradiction.
That's a big contradiction.
No, it's not.
There's no
When you sit here, you see him in that direction. When he sees you in that direction. So that's a contradiction.
He's
not getting shorter, you're seeing him shorter.
You are doing
In
things
special
in different reference
relativity,
frame.
you can see different effects in different frames,
Yeah.
when you're even dealing with two frames.
But they're not being
The
foreshortened.
a good example of this is
That's right.
the muons that
Yes, that's what I'm saying.
come from the
Yes, I'm
heavens
saying there's no
up there
foreshortening. It's apparent.
and penetrate our atmosphere. The muons are traveling nearly at the speed of light as they hit our Earth atmosphere. And on our Earth, these muons have a set decay time. You know, they radiate out. So have different half-lives. So on the say the laboratory here on the Earth sees the muon coming down and it's traveling at near light speed, and it the time that of the half-life that they observe is much longer. So you're observing time dilation as it comes down. Now, if you were stationed on a muon and coming down with it, you would see the Earth coming up at nearly light speed. And the muon would see length contraction. And so the atmosphere would go from there down to there, and it would travel that short distance in a little time, from his point of view.
Just a comment in relation to what Bill said. I looked up Wikipedia, and they talk about the effect of the sun. They talk about the ablateness of the sun, and I presume that's a factor because the ablateness is at the
Right,
angle.
and also the electromagnetic fields of the sun.
Well,
It has a
it
north
gives
pole
this
and
one,
south pole.
and it only has 0.025 seconds of arc, so it's quite small. It's less than 1,000th of the 43, so that one is pretty negligible compared to what you're doing.
That was a quick correction, a quick fact checking.
Bill said, yeah, well, I had noticed it earlier, you see, so when you look it up again. So the fact that the sun's axis is tilted relative to the orbits of the planets, and the sun has got some ablateness, that's the thing, so some of the masses above and below the plane is not symmetrical, and it only comes to 0.025 seconds of arc. So out of your 43 seconds, it's less than 1,000th of that. So it's not upsetting your result at all.
And also the velocity of the planet is changing in its orbit, and the acceleration is changing in the process.
He's without for the velocity changing.
Pardon?
He's done the
No,
velocity.
he hasn't done the acceleration because the acceleration is different at the ends of the semi-major axis for the orbit. He's not taking into account any of those variations.
Yes, he is. It's calculated at every point for all the points around the orbit.
Well, the velocity changes at the end of the orbit, and that's due to acceleration, but I just calculate whatever the velocity is at that point. I calculate the velocity by using the potential energy and the kinetic energy at the perihelion, which is given in the physics notebooks, and juggle that between the two.
Another idealization you use is you use for the gravitational mass gamma, m, and experimentally the ratio of two masses. If you take the ratio of two inertial masses of the same two gravitational masses, they're equal, but the masses themselves are not equal. They don't obey the same law. Okay.
Where the heck, go straight into the members meeting? Wake Jim up.
Well,
Sorry? Wake Jim up. Jim! We're gonna have a members meeting.